So we've been studying polynomials and especially irreducibility and reducibility of polynomials. It's time to move on to a new chapter. We're not going to be focusing on polynomials, but polynomials will absolutely, most definitely come back, and we'll be seeing polynomials show up here and there, in fact, quite a bit in the rest of this class. So we can't forget what we learned about that, but we are going to move on to a new chapter. So this is chapter 26, and this is ring homomorphism. And, you know, I think your book calls it factor groups, but I prefer to say quotient, or I just said groups, didn't I? Rings, factor rings, but quotient rings. And I'll just put it in parentheses, factor rings. Right, so we're going to study homomorphisms, and then we're going to study quotient rings. Remember when we studied the same topic for groups, right? We talked about quotient groups, right? There is an analog, right, of that in the ring theory, right? Quotient rings. So we already have this definition. We've defined what a homomorphism is, but I just want to remind you. So let's let R and S be rings. A function phi from R to S is a, and I'll just put it in parentheses, ring homomorphism if a function respects both addition and multiplication. So if for all R and R hat in capital R, two properties hold, right? The first one, phi of R plus R hat is equal to phi of R plus phi of R hat, and also needs to respect multiplication, so phi of R, R hat equals phi of R times phi of R hat. And of course you want to remember from context, right, what these different things mean. So for example, right there, that plus sign means the addition operation in R, while that plus sign means the addition operation in S. Same thing here. This is multiplication in R, this is multiplication in S. In the case that phi is a bijection, then we call it an isomorphism. So if phi is a bijection, then phi is an isomorphism. And in that case, so then we write R, and then our same isomorphism symbol there, so R isomorphic to S. Now, so you've already seen this definition, but since we're in the homomorphism chapter, it makes sense to have this down and just remind everybody this is what we mean by a homomorphism and an isomorphism. A couple of things that you showed, so in homework, you showed well, you showed the composition of homomorphisms is a homomorphism, and the inverse of an isomorphism is an isomorphism. So you showed the first one, if we have this setting right here, so let's say R goes to S, goes to T, and we have phi and psi. So if phi and, well, let me just write it like this. If these are homomorphisms, then the composition psi of phi is a homomorphism. And in fact, let me write it with using this diagram notation here. So then psi of phi is a homomorphism. And also, if we have if phi is an isomorphism from R to S, then phi inverse is an isomorphism from S to R. Right? So we know these two facts right here. Let me give you a few examples of ring homomorphisms. These are the important ones that we'll need. And we've seen some of these already, or we've seen at least a couple of these. So one of our primary examples here, so evaluation at alpha. So remember how that goes. So we would have F is a subfield of E. So let me just write that like that. So F and E are fields. F is a subfield of E, and alpha is an element of E, right? Then phi sub alpha from F bracket X to E given by phi sub alpha of F of X equals F of alpha, right? That's a homomorphism. The other important one, so this is going to be a crucial one. Right, we'll definitely make use of this in the near future. And another important example, reduction mod n. So that would be phi from Z bracket X to Z sub, I guess we can just do Z sub M bracket X given by phi of F of X. And remember, we'd use this notation F bar of X. So what do? You reduce the each of the coefficients of your polynomial, mod M, also homomorphism. Right, so these are two important ring homomorphisms. We're going to make use of these. We already have seen them. Here's another example. This is one that we haven't seen, so let's let Z bracket root 2. This is going to be the set, and we've seen this bracket notation on the homework, kind of a common ring theory and field theory notation. So this is the set of all things in the form A plus B root 2, where A and B are integers. And let capital R equal the set of matrices, so these would be 2 by 2 matrices of the form A, 2B, B, and A, where A and B are integers. Now, you can check that both of these are rings, right? So you can check. And you don't want to go through all the axioms. What you want to do is do the sub-ring test. So you can check that Z bracket root 2 is a subring of R. And also R is a subring of M2. And you can put whatever you want there, R or Z. I guess here in my notes I put a Z here. All right, so the ring of 2 by 2 matrices with entries in Z. So this one's a ring, this one's a ring. And now what I'd like to do is actually show that they're isomorphic. So let's consider the function phi from Z bracket root 2 to R, defined by phi of A plus B root 2 equals the matrix A to B, B, A. Now you can go through the steps. I mean, it's kind of rigged to work out. So I'll just say check that phi is an isomorphism. Right? It's very straightforward to verify each of the steps here. And so what? These two, sorry, I kind of erased this. But I mean, when you first look at this one and look at this one, they don't necessarily, to me, look like they're the same, right? There's this square root of 2 thing, but we're looking at sort of certain set of real numbers here. Here we're looking at matrices. But now it's kind of an amazing thing that algebraically these two sets, or these two rings, are indistinguishable. So there's a few examples of ring homomorphisms and isomorphisms. And now we've got a theorem. And what I want to do is collect a whole bunch of properties of ring mappings, ring homomorphisms, all in one place. So this will be properties of ring homomorphisms. So let's let phi from R to S be a homomorphism. If you want to insert the word ring in there, that's fine. And so I'm going to write a bunch of properties down, and we will prove a few of these, leave the rest as exercises. So part A is that phi of 0 equals 0. Part B, if R is an element of R and N is a natural number, then phi of R raised to the N is equal to, oh, you know what, I want to say the additive version first, sorry. So then phi of N dot R is equal to N dot phi of R, and phi of R raised to the N is equal to phi of R raised to the N. Part C is if R is in R, then phi of minus R is equal to minus phi of R, right? So what does that say? It says that a homomorphism, this one, sorry, I'm kind of jumping around here. This one, obvious. This one is saying that homomorphisms do what they're supposed to do with respect to applying the operation multiple times. This one right here tells us that homomorphisms take additive inverses to additive inverses. Part D. If A is a subring of R, then phi of A is a subring of the codomain S. So that was D. So part E. If B is a subring of S, then the inverse image of B is a subring of R. And then there's 3 more here. So the next one, if R has unity, then phi of 1 equals 1 in phi of r. Now, we need to be a little bit careful. What is this saying? Okay, so first of all, I do not mean the number 1 in any of the situations here. So what is this saying? It's saying that if R is a ring with unity, then the image is going to be unity in phi of R. Not necessarily in all of S, but in phi of R. Okay, so unity goes to unity, but it's unity within the image, not necessarily the entire codomain. Next one, so phi is 1 to 1 if and only if the kernel of phi is trivial. And then the last one, so let's say part H, if R is commutative, then the image phi of R is commutative. Okay, so let me just talk about a few of these and then we'll prove a couple of them. Okay, first of all, let's see which ones we need to prove and which ones we don't really need to do anything. This is true because phi is a group homomorphism with respect to addition. And group homomorphisms take identity to identity. Right? So there's nothing to prove here. We already proved this in Math 481. Same thing here. You just prove this by induction, essentially. Same thing here, right? This basically follows by induction and the definition of homomorphism. This one, I guess there's something to prove. Maybe we'll do this one right here. This proof, what would you do? Just use the subring test. This one also, use the subring test. This one, you just go by the definition. This is true because of group. You know, this follows from Math 481. And then the last one, this is pretty straightforward. So I'm just trying to identify which ones I want to prove. I wish you were here because then you could say, oh, I want you to prove this one and that one. So let me just pick, I guess I've done a proof like this already in 481. So maybe, how about if I do, I don't know, how about E and F? Right, so yeah, I'm going to do parts E and F. And the rest I'll leave for exercises. A good chance that some of these will, or one or more of these will show up on the midterm. So, you know, maybe it's a good place to practice. Okay, so for part E, so let me just remind myself what I'm proving. So this goes like this: if B is a subring of S, then the inverse image of B is a subring of capital R. Okay, so what do I need to do? Well, to apply the subring test, I need to show that it's non-empty, closed under a subtraction and multiplication. So first, since phi of 0 equals 0 by part A, it follows, oh, and I should say, and 0 is an element of B, we see that the inverse image of B is non-empty, right? 0 is in there. Okay, so now let's show that it's closed under subtraction. So let's let, say, x and y the elements of the inverse image of B. So what does that mean? So then, phi of x is an element of B, and phi of y is an element of B. So now, what do I need to do? I want to show that x minus y is an element of the inverse image of B. So if I look at phi of x minus y, that's equal to, well, what is this equal to? This really means phi of x plus minus y, which, because we have a homomorphism, that's phi of x plus phi of minus y. Now I need to use part C, right? This is equal to phi of x minus phi of y, so that's by C. And now this, and oh, that sucks. Okay, so let me do it like this. This is an element of B. So, and then this step is by C. Right, so what just happened here, we know that phi of x lives in B, we know that phi of y lives in B. B is a subring, which means that it's closed under subtraction, so this element, right, has to live in B. So therefore, x minus y is an element of the inverse image of B. Also, if I look at phi of x times y, that's equal to phi of x, phi of y. That's an element of B, because both phi of x and phi of y are elements of B, and we know that B is closed under subtraction, under multiplication. Therefore, what xy is an element of the inverse image of B. So by the subring test, phi inverse of B is a subring of R. So that completes the proof of part E, and then let's also look at part F. So let's assume that R has unity, and then I want to show that phi of 1 is unity in phi of R. So pick, let's say x in phi of R. Then if I do, well, so what does that mean? So that means that x is equal to, sorry, that should say capital R. So then x is equal to phi of little r for some little r in capital R. So now, if I look at phi of 1 times x, that's equal to phi of 1 times phi of r, which is equal to phi of 1, I should use the phi of 1 r, which is equal to phi of r, which equals x. In other words, when I multiply x on the left by phi of 1, I get x. Same thing, so similarly, x phi of 1 equals x. That's what we need. phi of 1 behaves as, right, the multiplicative identity within phi of r. Right? When you multiply, you get x. Okay, so the rest of these are left as exercises, and I can almost guarantee you at least one of them is going to show up on the midterm. So this is a good place to get some practice in proving this stuff. Let's see how we're doing on time. Yeah, we'll do a little bit more. Okay. So a little bit of notation. So let's let capital A be a subring of R and little r be an element of R. We're going to define well, we're going to define three things. So R plus A is equal to the set of elements of the form R plus little a, where little a runs through all of capital A. And that looks like a coset. We're going to define R times A equal to the set of objects of the form R times little a, where little a runs through all of capital A. And then we're going to do it in the reverse order also. A, R equals the obvious thing. So now that we're working with rings, and we've got two operations, there's really two different things that we could view as cosets. Right? And so we're going to use this notation here. So now, a definition. And this is going to be, oh no. Oh yeah, sorry, first a definition. So a subring capital I of R is an ideal of R if for all R in capital R, Ri is contained in I and I times little r is contained in I. So this is kind of an interesting condition here. What does it say? So we take a subring, all right, and so an ideal is a special kind of subring. It's the kind of subring that is closed, and closed is not quite the right word here, but I'm going to use the word closed under external multiplication. If I take somebody, of course, if I take somebody inside capital I, if I take two elements of capital I, because I is a subring, right, it's closed under multiplication. So now what we need is the interesting part is if we take somebody that's outside of I and we do this multiplication and we land inside of capital I. Right? So if it works on both the left and the right, then we call it an ideal. And we're going to go straight to a theorem here. And this theorem has a name. It's called the ideal test. So it goes like this: a non-empty subset capital I of R is an ideal of R if and only if two things happen. A minus B is an element of I for all A and B in capital I. So it needs to be closed under subtraction. And the second, for all would I use little r? Yep. For all little r in capital R and little a in capital I, we have RA is an element of I and AR is an element of I. Okay, so we need to prove this. In the forward direction, what do? We assume that we've got an ideal. What do we know about ideals? Well, ideals are subrings. Subrings are closed under subtraction. And by definition, right? So we know it's subring, so the closed under subtraction part has to happen. And then, by definition of ideal, both of these properties have to hold, right? So there's nothing to prove here. I don't usually do this, but in this case, I think it's legal to just say this is obvious, right? It's just straight from definitions. In the reverse direction, so we have a non-empty subset, and we want to show that it's an ideal based on these two properties right here, and I don't know, what is there to do? How do I want to write this in, so let's say it like this. 1 plus 2 show that our I is a subring of R. And so notice we've assumed that it's non-empty. To show that it's a subring, it needs to be closed under subtraction and closed under multiplication. Well, this assumes even more, right? So 1 plus 2 show that I is a subset of R, or subring of R, where we restrict little r to capital I. That shows that it's closed under multiplication. And then yeah. Okay, so then I mean, this is just another way of saying these two things right here. So 2 shows that shows is not the right word. 2 forces gives us is fine. Gives us that Ri contained in I and IR contained in I. I mean, this is just another way, or this part right here is another way of saying that stuff right there. All right, so there's really nothing to prove in this case. So let's see. Oh, a little bit of terminology, I guess. How are we doing on time? Yeah, I guess we got a couple more minutes. So let's do a couple of examples here. So for any ring R, the set consisting of just 0 is an ideal of R. All right, this is the trivial ideal. And you can verify that. I mean, it's just a straightforward application of the ideal test. What else? Oh, and I guess I should continue. So we could go like this. And also R is an ideal of R, right? So anytime you have a ring, the trivial ideal is an ideal. Also, R is an ideal of itself. In the case that I is an ideal, but it's not equal to R, then of course we call it a proper ideal. So if if I is an ideal of R and I is not equal to R, then I is a proper ideal of R. Oh, one thing you might ask, well, is there a symbol, right? Rather than having to write out the word R, I is an ideal, there's no nice symbol for ideal. It's unfortunate, right? So there is a sub-ring symbol, but there is no nice ideal symbol. I'm going to do a couple of examples. So if n is a natural number, then nz is an ideal of z. And let's actually prove this using the ideal test. So clearly nz is not empty. Yeah, obviously. In certain situations, it's really, you don't even have to write this sentence down. Of course it's not empty. So let's pick, how about A and B in NZ and R in Z. So now, what do we need to do? We know that it's not empty. We need to show that it is closed under subtraction and under external multiplication. So then A equals n times k and B equals n times m for some k and m and z. So now, if I look at A minus B, that's equal to n times k minus m, which is an element of nz. So the difference is a multiple of n. And r times A is equal to r times nk, which is equal to n times rk, which is an element of nz. Right, so we showed that it was closed under subtraction and multiplication from outside or possibly outside of NZ. So by the subring test, NZ is an ideal of Z. And one more example. So let's let F be a subfield. So here are fields of E. And then I need alpha in E. So let's say and let alpha be in E. Now what I want to look at, we'll say claim the set capital I, which is the set of all polynomials. So F, polynomials with coefficients in F, such that F of alpha equals 0. So the claim is that this set is an ideal of F bracket X. And now you might see why, or see why we might be interested here, or where the connection comes from, look at what we're doing. We're looking at roots of polynomials. And so the set of all polynomials that have this particular alpha as a 0 turns out to be an ideal. Let's go ahead and prove this. So first of all, it's non-empty because this is true for the 0 polynomial. So let's say let's say proof. Note that 0 is in capital I, and so I is non-empty, right? And when I write 0 here, I mean the 0 polynomial, right? If you plug alpha into the 0 polynomial, you get 0. So now, let's pick f of x and g of x in I, and say h of x in f bracket x. Then, if we look at f of alpha minus g of alpha, that's equal to, well, 0 minus 0. And so f of x minus g of x is an element of a capital I. And if we do, say, h of alpha times f of alpha, that's equal to h of alpha times 0, which equals 0. And so, h of x times f of x is an element of capital I. So by the ideal test, capital I is an ideal of f bracket x. Okay, that's a good place to stop, so we'll see you next time. We'll continue our study of ideals.